what do we mean when we say odd and even functions? Well, what do we mean when we say odd and even numbers? When we say odd and even, there are two categories that help us to say some numbers, they're special, right? Some numbers are odd, some are even, some are, neither, right? You got weird numbers like, say, 1.5 is that, okay? So not all numbers fit into these categories, but the numbers that do, they're useful and they follow a lot of rules which are helpful to us, okay? Now I'm going to leave it to you, and I'm going to ask you this next week, to try and work out, okay, I know what these are, and you're going to know what these mean after I finish talking here, but why are they called those? Like these really don't have that much to do with these. Why are they called odd and even functions? Why do we give them those names? Okay, so I said they're categories. These are categories, this is worth jotting down. Categories for describing functions according to their symmetry. Symmetry is the key. Now, right off the bat, you can see a similarity. Like I said, some numbers are odd, some are even, and some are neither. In the same way, some functions are odd, some are even, and some are neither because they don't have any kind of symmetry, right? So odd and even functions are actually a very special sort of subset of all the functions out there, okay? And you already know tons of odd and even functions. We just haven't given them the names, okay? So let's start with even functions. What kind of function has even symmetry? Well, y equals x squared. Just draw yourself a really small one of this. Here's your exception to the rule. We don't need to put any details on here. I just want you to see it, because immediately you will see the symmetry. Right? This is an even function. What kind of symmetry, how would you describe the symmetry that it has? Yeah.
About the y.
Yeah, good. So if I took the y-axis, put a straight line there, right? Oops, sorry. Very straight, okay? You can sort of imagine it like a mirror, okay? And what do mirrors do? They reflect, okay? So another way to say this is it's reflectional. That's the way to describe it. Reflectional symmetry. And importantly, it's always actually got to be around the y-axis. This part's really important. If I were to take this graph, right, and move it over a little bit, say to draw y equals x minus 1 squared. Okay, same graph, what difference? Yeah, good. The whole lot, including its axis of symmetry, has moved over 1 unit. Yeah, you get the idea. Okay, now, here's a funny thing, okay? And hopefully this will shed some light on why it's uneven. This function still has a kind of symmetry, but it doesn't have this kind of symmetry because it's not around the y-axis, it's around some other place, okay? So all of the functions we're going to look at are around there. Can anyone think of any other even functions off the top of their heads? Yeah. Ah, good. So, as an example, intrigue, okay, when you draw this out, okay, what do you got? You've got this part, this is the part that you're used to, right, because that's 0 to 360, 0 to 2 pi, which you draw a lot, but of course you can go the other direction, and again, it's got that reflection that you can see, okay? Before we leave off this, those are the most common examples. You can really take, though, any polynomial with an even power. So I could say, you saw before, x to the 4, also even symmetry. X to the 6, x to the 8, x to the 800. They'll all be even. Okay? I'll let you have a think about why in a second. Now there's my visual definition. I think you guys could now pick out an even function or not. I want to give you an algebraic definition as well. So visual, algebraic. Now when I give you the algebraic definition, you might think, why are we using this? Because it's so much more intuitive and common sense. Like even a very young child could understand this. What I'm about to give you will be weird. Okay? The reason why I'm going to give you this is because this kind of is not very good when you want to prove something. Like someone says to you, okay, prove that this is even. And you're like, well, it kind of looks like the thing, like go from this side and then go from that side and it's the same, right? Well, that sounds airy-fairy and not really proof quality, okay? But this is, okay? So what does it mean, algebraically, for a function to be even? It means if a function is even, then that function, when you put x in, will be exactly the same if you put negative x in. Does that make sense? So this example, easy. Put 1 in, you get 1. You put negative 1 in, you still get 1. These things will always be the same. Okay? That's the algebraic definition. When you look on the sheet that you've got at the moment, it says prove this. Okay? You're going to have to do it using this fact. Okay? This is where you want to arrive. So, as an example, to prove a function even. Let's consider y equals x squared, or f of x equals x squared. I want to prove that it's even. There's my f of x. I know what this side looks like. I know what my left-hand side looks like. I need my right-hand side. Okay, that's what I'm required to prove. So I'll say f of minus x equal 2. Okay. Now, if you wanted to be cheap, you could say, well, that's x squared, right? But of course, a proof means show me the logic, show me the steps. Don't take shortcuts, right? So in fact, this is why we looked at function notation, right? If I'm saying f of that, it means everywhere I see an x, I'm slapping a minus x. Okay? And it may seem a little excessive to put in this, but again, I'm trying to make the logic obvious. Okay? And that's equal to x squared. That's equal to f of x. So you can see, there, I'm done. Right? So you can say, therefore, f of x is even. Done. Okay, that's what you'll be doing on that sheet. Now, even symmetry. What is odd symmetry? Odd symmetry. Now, you might think, well, another option, right, would be around a different axis, okay? Part of the problem with that, though, is that if it were around, say, the x-axis, and we've got a bunch of functions like that, like, say, the circle, or that sideways parabola we looked at, right? The problem with it is, well, it's not a function, right? To be symmetrical around that way, it would have to be a relation, because you've got to get multiple outputs for the one input, right? So instead, odd symmetry, another M. I'm good at spelling. Okay. My example of this is not y equals x squared, it's y equals x cubed. Okay. So here's my graph. Let's try that again. Let's draw that first. That was cheap, but it worked. Okay, now, we talked before. We said this has a symmetry, but it's obviously not the same. There's no, and you can't pick an axis about which you can say, oh yeah, it's that axis, or that axis. Even if you're like sneaky and go at an angle, okay, it still doesn't reflect across. Like if I took, where's my ruler? My ruler's stuck in the door, okay. If I said y equals minus x, put a line through there, okay, and you twisted your head and you reflected one part of it, you wouldn't get the other side. Can you see that? In fact, for instance, if I were to reflect this part, I would get this. Okay? It's not the function I want. So what, we agree it has a kind of symmetry. What kind does it have? Yeah. Yeah, that's right. So you've seen this before. Like in year 7, we looked at different kinds of shapes, right? There's two names for this. We can say it's symmetrical about a point, so hence point symmetry. I think an even more intuitive way to say it is if I, instead of flipping it, reflecting it, right, so that's my physical action, I could take this shape and I could twist it, I could rotate it around, couldn't I? I could take this half and spin it around and you'd get the other half, right? So you can also call it rotational symmetry. Okay, I think that's more intuitive to me because I'm like, point symmetry, what about the point? Okay, whereas rotation is like, oh, I gotta turn it. Okay, both are fine. Okay, now I gave you an algebraic definition for evenness before. Okay, So what do you think would be an algebraic definition for oddness? Let's see. Odd. Now, I left this all on here because it is super, super close. The definition for oddness and the definition for evenness. You still got the function, and it has a relationship to the function when you put the opposite value in. But it doesn't have the same relationship. They're not identical. What's the difference? It's flipped. That's it. Okay. So some people find this a little confusing because they are so similar. All right. So maybe you want to put this in like a different color or something like that. If I wanted to prove the function were odd, for example, y equals x. Let's do a different example because that's boring. X cubed. There's one example. Can someone give me another one? X over 5. Okay. This is interesting. All even powers are even functions, and all odd powers are odd functions. Now, that's interesting. It's not the reason they're called odd and even functions, but we'll get to that a bit later. Can anyone else think of? Are there any kinds of other functions you know about that follow this kind of thing? Okay, we had cos x before, so in trig terms, you could use sine or you could use tan. Both of them have this same kind of symmetry. Because, okay, can you see it? Do you get it? So let's go with sine x. Y equals sine x. How would I prove that it's odd? So I should probably say f. Okay. I would say, well, if that's what f is, what's f of minus x? Well, I'm just going to replace every x with a minus x. Okay. And unfortunately here, you can't really, it sort of does look like black magic if you're looking from the outside. You guys know, as an identity, that that is equal to this, right? That's one of the ones you learn very early on, okay? So that is negative f of x. There's not really many steps of logic you could put in here, honestly, okay? So that's that. End of proof. Okay, I'm done. This is the format it's going to always look like. You've got f. Tell me what f of minus x is and do whatever algebraic stuff you need to show this. Okay?